All right. Hello, everybody, and welcome to another lecture in our play matrix analysis. My name is Germán Garcia, and today we are discussing classification and evaluation. Now, when we are working with datasets, it's common that they are captured in classes or in different sets. For example, if you're measuring petal lengths for different flowers. And so there is this interest in being able to tell from our dataset only whether or not all data lies where it should. That's what classification and clustering do. Basically, today we're going to be looking at the Simca and LDA, Simca being short for soft independent modeling of class analogy, and LDA being linear discriminant analysis, a very interesting application of quadratic forms to this problem. And in the end, we'll discuss evaluation and other common methods. Now, the idea behind classification and clustering is to group data into multiple groups such that data in those groups are similar but different to those in different groups. Like find out common features and use them to discriminate the data. However, they don't share exactly goals, and so when we cluster, we first divide the data into groups and then try to interpret the results, while in classification we already have the interpretation, namely we are working with different flowers, and what we are trying to find is the class belonging of every observation given that interpretation. So basically, clustering wants to answer questions are the patients with the same disease? Are there different types of patients that need different treatment? While classification aims to answer questions such as, using some test, can we find out if a patient has or not the disease we are talking about? Now, typically, when solving a classification problem, we need some data to train our method on, namely observations where we already know which class they belong to, so we can test the method before. That's what is called training in this sense. After training the method on this data, we hope to be able to use it on new data with unknown classes. That's the main use of these methods. Usually, finding the class itself is very time consuming and or costly, or maybe not possible at the time we collect data, while the data we got for the observations is much cheaper. I mean, we have to observe it and that's it. Another thing we must keep in mind is that the data classification used to train is not always complete and is not always good quality. If it's good quality and it's complete, we will call it a gold standard, but that's something that is bound not to happen most of the time. Finally, the training data is incomplete or the classification the training data is not fully reliable, we will call it a silver standard. Wants to be gold, not quite there. And so today we're going to take a look at two different classification methods, Simca, which is a method based on principal component analysis, and LDA, in which linear discriminant means that we want to find a line such that when we project the data, it separates the two classes. Since the first one we are doing is Simca, I'm going to do a quick overview of the principal component analysis using the covariance method as we saw in the last lecture. So step 1, we remove the mean from every individual set of measurements and order the measurements as the rows of matrix X. Step 2, we calculate covariance matrix M. Step 3, eigenvalues and eigenvectors of M, it's a square matrix, that's no problem whatsoever. Step 4, we choose the amount of eigenvectors that include, for example, enough to keep 90% of the variance, that's usually common threshold. And in the end, we calculate our new dataset using data matrix X and the matrix composed of our principal components. Now that we know this, what is Simca? Soft independent modeling of class analogy is a classification method based on PCA. This is pretty common, for example, in chemometrics, and we'll see why. Simca is a soft classification. I mean, it allows a single object to belong to more than one class. in the case that we have plenty. Some objects can end up with no class, either indicating a potential new class or more commonly an outlier. In the example we're going to be seeing, we're working with different flowers and there are some outliers out there. Now, Simca does not imply that clusters have any specific shape or distribution of the clusters for each class. It only classifies. However, the description of the class of Simca is tied to the ability to describe classes of PCA, and as we will see, Simca is going to have some problems with certain shapes of cluster. We have data gathered around an S that's going, for example, to give us a lot of trouble in the future. But now, what is Simca? What do we do? So basically, we do any preprocessing, namely filling the missing data and all that. Then we calculate principal components for each class and pick the suitable number of components. Then we choose a confidence level because we have to calculate some statistical measures that we will use to classify the new observations. And in the end, we assign new observations to a classes using an F-test that will tell us the quote marks distance in the PCA sense from each class. Now, step 1. In this step, we do all preprocessing. Missing values, outliers. Please do not standardize the variables. Please do not standardize the variables, because that would definitely alter the shape of your classes if you're still able to do so. And if there is other preprocessing of the data needed, we can just do it in this step. This is why preprocessing is called a pre, because it's always the first step, the thing we do before getting into matter. Now, we're performing principal component analysis. So for each set of n observations, namely XL1 to XLn for class L, we calculate the covariance metrics, find the principal components, and choose a suitable number of principal components to represent the class. Now, let's expand a bit on this. For each class, we have P original variables, K principal components, N observations, and the loadings matrix WK with the eigenvectors. So for each observation in the class L, we calculate the projection of the observation onto the mean. This is the mean vector, overall observations of the class, and this product times xil minus the mean vector. This is how we project the observation onto the mean. Next step, we calculate the distance from the observation to the projection using this calculation. Here, we use Euclidean norm 2 for this step. And now that they have these distances, we can proceed to calculate what is called within class variance. Within class variance is this sum, the sum among all observations of class L of the distance between each vector, each observed vector and the mean vector squared. And here we have number of original variables minus number of principal components for that class, and of course observations minus principal components minus 1. So this is within class variance. For step 4, for each observation y sub I, we look at each class and decide whether or not it belongs to that class. So we take class L and calculate the distance from the observation vector to the class mean, to this x bar vector. With this we get a projection, we calculate the distance from vector to the projection, and then we calculate the variance in this way as the distance of the observation squared divided by the number of original variables minus the number of principal components. Now, to decide if the observation should belong to class L, we perform what is called an S-test. an f-test. In order to perform an f-test, we calculate this quotient here. Here we have this variance, and here we have regular standard deviation. And now we compare this value with the quantile of the F distribution with this amount of degrees of freedom and the chosen confidence level, as you can find in any table. Literally, if you Google F distribution table, you can find that there will be one available for you as well. Now, if the calculated value, this value here, is smaller than the quantile of the F distribution, then we assign the observation to the class. If the calculated value is larger than the value in the table, then we can't assign the observation to the class. Now, details. An old man of my village used to say the devil lies in the details. And so there's some things we have to take care of. Now, the confidence level can be seen as the probability that an observation belonging to the class is classified as that class. So, a higher confidence level means that it's easier for an observation to be classified into the class. Second consideration, for more in-depth understanding of the statistics involved, it would be ideal that you check upon other courses, like for example time series analysis, or the basic course in statistics, since many of the tools that we are implicitly using here as the F-test, there is a ton of statistical firepower there that we really don't have time to get into. And you may find it interesting. So if you want more knowledge, please leave a comment, and I will link you with more thorough explanations on the tools. Now, third detail. There's more sophistication versions of the method, variations of the method, where not only the orthogonal distance is used, but also we can use the distance along the principal component, which results in sort of a box, cylinder, and ellipsoid around the mean. Certain shapes appear there. Now, we have already seen the math. Now we're going to do the math. So imagine that this, in the y-axis we have sepal width, and in the x-axis we have sepal length, and we have 3 flowers. I think I want 2 slides in a row. No. So we have 3 flowers, blue flowers, red flowers, and this one with the rhomboids here. In order to have something to test on, we will only train the method on the first 40 observations of its type, which leaves 30 other for testing. So firstly, we will show the procedure from one of the classes, namely flower setosa, and the others are proposed as exercise as they can be done in the same way, and it would be highly redundant to go on this. Now, we start by extracting the 40 observations belonging to the class and calculate the covariance matrix in order to calculate principal components. So, covariance matrix. Square matrix, 4 times 4, everything is going all right. Now we calculate the eigenvalues of the covariance matrix with the eigenvectors as the columns of V and the eigenvalues as the elements of this vector. So you have eigenvectors and eigenvalues here. If we sort the eigenvalues from largest to smallest, we calculate the proportion of total variance that they explain. We have that if we only pick the third vector, we explain 0.765 of the variance. If we pick third and second, we explain 0.898. If we pick up 3, we explain 0.976. Ideally, we would want to keep 3, but since keeping 2, we already have almost 90% of the variance explained, we're going to keep only 2. So vectors 3 and 2. Third eigenvector, second eigenvector. So we pick up the 2 principal components and we get this loading vector here. Now we want to calculate the within class variance in our set. In order to do that, we calculate the projection of the observation into the mean, using the mean over all observations in the original p variables, our matrix W set, its transpose, and this distance here. And so for the first observation, what we get is this thing over here. We don't include W set here because otherwise the equation wouldn't fit the page. And what we get is this column vector here. Now, using that, we calculate the distance for each observation. Ideally, we begin with the first observation. Yep. And what we have, this is a norm 2, Euclidean norm, regular norm of this vector different. And what we have is this distance vector, in which the distance is the norm 2, so we calculate it, and we get 0.1048. Now, if we proceed for all observations within the class, then we think class variance can be seen by solving this equation as 0.0162, where we have to take account of the details here. The number of observations n set is 40, the number of features is 4, and the number of principal components is 2. So now that we have already gone through the process, we have to start with this next step, which is try and use this trained method to classify new observations. So let's pick two observations. This is the first one, this is the second one. We know the first is of Setosa and the second one is of Virginica from the test set. Remember that we have 3 different flowers. So firstly, we calculate the distance to the class mean. We have using this equation. We calculate for both this and this. Here set stands from Setosa, by the way. And what we get by following this process here is that the distance of the first observation to the Setosa projection is very small. In the second one, it's much larger. So we calculate the variance for the Setosa class. What we get is first variance is 0.0071, second variance is 3.3365. Now one is very small, one is very high. This already gives us a hint that one of them is obviously from Setosa and the other one is obviously not from Setosa. And now that we have this, we can perform the F test by calculating this statistical here. And we get two different parameters. Here, well, there is S1, there should be S2 z squared divided by S z squared here. And so we get two different statistics, T1, which is this over here, and T2, which is this not so little boy anymore over here. By choosing our confidence level as 95%, we go to the F distribution table, and by picking this exact amount of degrees of freedom, we have here 2 and 74. And if you go to a table for the F distribution with 2 and 74 degrees of freedom, confidence level of 95%, we have 3.125 as a threshold. So now we analyze our two statistics. The first one is clearly smaller than the threshold, so we can assign our observation to the class Setosa, and the second one is much larger than the threshold, so we cannot classify it as Setosa. So the first one goes in, the second one goes out. Now we can repeat it for the whole set, and in this case we would check that the binomial classification Setosa or not Setosa is fairly precise. It works surprisingly well. In case of other two types, if you, for example, let's go to the dataset again. This is Setosa class. The red one is Virginica, and the black one I don't remember the name right now. But if, for example, you wanted to discriminate these two classes here, we would probably had a much harder time. Now, if we pick those two, black and red, this method will sometimes classify observations as both and sometimes classify them as neither. But overall, the accuracy is pretty good. Pretty good. So at this point, it can be useful to try and change the confidence level and see if a better classification can be gained. Sometimes, especially where the classes are kind of blurry, it's good to maybe lower the confidence level and see what can happen. Now, in order to visualize this, we will use what is called a confusion matrix. A confusion matrix is such a matrix that element in the ith row jth column is the amount of observations of class the row classified as class the column. What does this mean? It means diagonal elements represent correctly classified elements, while non-diagonal elements represent misclassifications. In this case, if we include the pairs in the columns, this is first one, second pair, third pair, this triple, and here those not classified at any class as the results. If we use classifier and apply the confusion matrix, what we get is that when we are trying to separate between two, the result is pretty accurate. So all those were classified well. Here, those there were observations of Setosa that were classified as no class. Here were observations of Ver that were counted as no class, and the same. And if we go to the last column, here we have, for example, one observation of Ver that was classified as no class. So this is how you interpret the confusion matrix. You may think I was confused. That's kind of the point of the confusion matrix. It does its work, and it does it pretty well. So this allows us, once we interpret it correctly, to visualize roughly how accurate our method is. Now, this wraps it up for Simca. If you want to go over the different flowers, please feel free to do so. And now we're going to change to linear discriminant analysis and see what this method offers. The objective here is to reduce the dimension while preserving as much of the information that discriminates the classes as possible. Now, we don't have a priority of preserving the variance, but instead we want to preserve the information that discriminates the classes from each other. This is also referred to as Fisher's linear discriminant. So we are going to assume that we have n d-dimensional samples, n1 of these samples belong to class 1, and n2 of these samples belong to class 2. Our aim is to project the samples x on a line, resulting in a scalar value for every sample. So the idea here is that elements in the same class will be smashed into the line and get close to each other. And of course, far away from other classes. In order to evaluate class separability, we're going to use something that is called the Fisher linear discriminant. It's a function, a measure, that when maximized will give us the best line. But first we need to look at mathematical background and firepower that we will need. Firstly, in the original space, the mean of a class is very easy to find. That's the definition of the mean. And if we project it onto our hypothetical line, what we get is that projected line is this product here, row vector w, and this vector with the mean of the class. And now we can use this to describe the distance between the projected means. The projected means of two classes, if you calculate the distance between them, it's the distance between W transpose times nu1 minus omega W transpose times omega 2. So calculating this distance between projected means is a really simple task. Of course, there is a small problem here in the form that we don't know what vector W is, right? Right. So let's see. Although the distance between the projected means might separate the classes well, it does not take into consideration the variance of the data. Now this is a problem. If there's a high variance in the same direction as the one we would get when maximizing the direction of the means, we could get bad separability. So in this case, all our classes would be kind of clustered. In order to solve this, we will look at the variance within a class, which is also called scatter, on the projected line. This is sample variance, basically, within the class. And so what we have is vector y. Vector y minus the projected mean for its class square. So if we want to use this statistic measure to relate different class, one thing we are going to do is to calculate the within class scatter. And that's defined as the sum of the variances or scatter of the different classes on the projected line. It's S1 squared plus S2 squared, both with this nice beautiful curve hat. Now that we know this, Fisher's linear discriminant is the function Wt of x such that this function here is maximized. Now this explains what we have taken time to calculate S1 squared plus S2 squared, and on the other side we have been calculating the difference between the projected means. The quotient between both, when maximized, it's maximized by Fisher's linear discriminant. Now, we look for a projection where elements from the same class are projected close to each other, and distance between the projected class means are far apart. Now, the problem of maximizing or minimizing a function is generally a derivative equals 0 type of problem. So we're going to try to write Fisher's linear discriminant here in terms of w, because this doesn't make much sense as a function of w. And so we proceed. Si squared, we calculate this. We remember that we are looking for our projected line. I is w transpose x, and this projected mean is w transpose the vector of means. So we can expand this, and what we get is this beautiful equality over here. You may already be looking at it as row vector, matrix, column vector. So yes, this is a quadratic form. So if we call this Si, this thing over here, and SW is S1 plus S2, what we get is the within class scatter is W transpose times matrix SW times W. And what's SW? Well, it's S1 plus S2, which is 1 over N1 minus 1 times this sums within class 1 plus the same within class 2. It's actually easier to It's actually easy to calculate. We have data and we have the mean. Okay, now that one of the parts of Fisher's linear discriminant already depends on W, we're going to look at the distance between the projected means. And what we get is a really interesting quadratic form in which our matrix is defined by mu1 minus mu2 times mu1 minus mu2 transpose. If we call that matrix SB, for an instance, what we get is that this is this distance squared. Sorry, this distance is the quadratic form defined by matrix SB. And so, if we combine both, we find quadratic form over SB, quadratic form over SW, and you may be thinking, Herman, this is a Rayleigh quotient. Yes, it is. And for this, we can find the maximum. How do we find the maximum? We set the gradient to 0. Derivative with respect of W of this function is 0. And if we try to solve this, I encourage you to try this. It's a pretty interesting 3-step calculation. We get that the vector that minimizes this function is this eigenvector over here. Eigenvector with eigenvalue j of SW minus 1 times SB. But moreover, this has a concrete solution. This is not, no, we calculate eigenvectors and then we try. No, we can absolutely determine a unique solution for this one. In this case, the solution, the vector that minimizes Fisher's linear determinant, is SW inverse times the difference between the mean vectors. We've really come a long way, haven't we? I mean, this method is actually pretty magical. Like we wanted to look at variances on predicted delay. We wanted to talk about Fisher's linear discriminant. Here we have projected means, here we have projected variances. And in the end, what we found is a simple linear algebra problem with the solution is a pretty easy to calculate matrix, time difference between two mean vectors. Now really, how much better can a method get? So for a quick overview of it, step 1, we calculate the mean of each class in this way. Second, we calculate within class variance. Step 3, we add the two within class variances, S1 plus S2. 4, we calculate the vector that minimizes Fisher's determinant, which is this minus 1 times the difference between the mean vectors, and we get 1 point on the line. In order to define a straight line, you need 2 points. The other point is the origin by default. Now we can classify a new observation x by projecting onto this line. Here we get a vector, we put it there. And the way we classify a new observation is choosing a threshold. We choose a threshold t, and all observations that give a value of y greater than t, we classify into class 1, and all the others we classify them into class 2. Please remember that this is not y coordinate, this is our vector times the observation, I mean the evaluation of the line to the given data, namely projection. Now, finally, the two classes have approximately the same distribution on the projected line. The mean of the projected means is generally a good choice. Like a good threshold is something you usually have to improvise, but well, if you can say that you have similar distributions, then the mean of the predicted means is really a good estimation. In the end, the worst thing that can happen if you choose your threshold correctly is that the confusion matrix will show that you were pretty wrong. Now, we have done this process for 2 classes, but it may be possible to do it for more than 2. Fisher's linear discriminant can be generalized for more classes, which will result, instead of finding a vector, we have to find a subspace of dimension c minus 1, where c is the number of classes we want to classify. The problem is pretty similar. Instead of working with one eigenvalue, we have to work with several. Another alternative is to classify every class itself with respect to the other classes, giving as many classifiers as classes you have. Like, literally, you make a method to classify whether or not an element belongs to class 1, another to determine whether or not the element belongs to class 2, and the same with all the classes, and depending on which class you want to check that your new observation is, you use the proper classifier. Now this is costly, but it's easy. It's a really nice approach to the concept of separating n classes. Additionally, you can use the classifiers of every single pair, which will be more precise probably. Now, linear discriminant analysis works very well for Gaussian distributions. However, other shapes, other types of distributions may put us in a really hard, tough, and not easy to deal with at all situation. For example, if your classes have the form of 2 C's that intertwine, imagine that your data is organized within the channel logo. That could make linear discriminant analysis have a really bad time. If both clusters have the same mean, you cannot classify them because Fisher's linear discriminant is 0. Now, if the information lies in the variances instead of in the class, it will also fail, which means we are assuming homoscedasticity in a kind of a subrepetition way there. There's a ton of hypotheses that we use but don't mention. Happens all the time. Now, there is another similar method which shares the same name, also linear discriminant analysis, in which we assume a Gaussian distribution and we use a probabilistic perspective for classification. But now, let's see how linear discriminant analysis works with an example. We're going to go back to the example with the flowers. This one, where we have setosa here. These red ones I think are called versicolor or something like that. Oh, there we go. In order to be able to plot the line separating the 2 classes, we consider the first 2 features: sepal length and sepal width, which are the ones we are working with. Now we have 100 observations out of 2 classes with 2 features each. This is the graph for it. Look at this point. It's an outlier. It's going to give us problems, but we will get there. So we start by calculating mean and variance for each class. Mean for setosa, mean for versicolor, and covariance matrices. Variance matrices. And so next step we calculate SW, it's this matrix over here. Calculate its inverse, of course. So the optimal line, the best line, is the one whose directional vector is defined by this times the vector with the difference of the means. So it's defined by these 2 coefficients. the slope of the line, it's not defined by these two coefficients. It goes through this point. This is one point, and the origin is the other one. Now, the slope of the line we project onto is as simple as the second divided by the first, variation of y divided by variation of x. So it's minus 1.23. And the orthogonal line that separates the two classes has minus 1 divided by the slope. So, in order to classify the observations, we will project them on the line y equal to our vector times x, and then choose a threshold t. Since we believe that we are working with similar distributions, we will choose the mean of the projected means for our threshold. That's minus 9.37. And so this is our plot. This is line data is projected upon. And this is the orthogonal line that separates the two classes. The way you see it, it may seem intuitive that the line that separates the two classes and the one you project upon should be the same, but no, they are orthogonal by definition. So yeah, we have that this line separates both classes pretty well, with, well, this point being kind of in between. And here we have our little outlier. So if we make the confusion matrix for this, we will get a certain number 1 there in column 1, 2. These are confusion matrix. As we had predicted, 1, 2, we have this flower setosa classified as versicolor. The other 49 observations went well, and all 50 observations of versicolor were fine. Only this point. Close enough. I mean, that's a pretty accurate representation. Now, while the confusion matrix is useful, it does not account for overfitting, which is essentially when the method is trained too much. There is really no easy way to avoid this, but if you have a lot of data, we might be able to simply train on one part of the data, one half of the data, and test on the other half. That, however, might not be an option if the data is small. Happens. But instead, what you can do is a process called leave one out cross-validation or n-fold cross-validation. Performing an n-fold cross-validation is simple, but it can be quite time-consuming. So this is what you do roughly. Step 1, divide your data into n random parts. Step 2, train to remove one of the parts and train your classifier on the rest. Step 3, test your classifier on the removed part of the data, the part of data that we have not used for training. And then we rinse and repeat for all the n parts, and in the end we take an average of the result. Now, it's also very useful to calculate the sample standard deviation of the same things you calculate in 4, as it will give us more information. But basically what we do is separate into n parts, take one out, test on the rest, train on the rest, and we do the same for all the observation. That only can be a really powerful tool if you're feeling that your model is actually overfitting. If it separates too well, it's sometimes because you train it with too much data, so it's already prepared to work with your data too well instead of being actually accurate for projections in this case. Now, some classifiers return a value rather than a class. In order to classify an observation, we have to check how high/low this value is and then classify it accordingly. One example of this, of the classifier returning a value, if we were working with Simca, we leave the choice to confidence level as something we want to optimize as well. then the classifier returns that value, that confidence level. This is pretty common when the cost of a misclassification is not equal. For example, if you're doing a medical test, you would rather have some extra false positive in order to avoid false negatives, as a false positive is probably bound to not kill anyone, but a false negative will. You know how this works. In this case, we have precision, recall, and F-measure as three really useful tools. Now, precision is the measure on how sure we can be that someone that is in class 1 actually belongs to class 1. Recall, however, is sort of the... I mean, it's dialectically speaking, it's the opposite, but mathematically not really. Recall is a measure on how large proportion of those in class 1 are actually classified as class 1. So it's correctly classified as class 1 divided by total number of class 1. Look at the difference. This is observations of class 1, but this is elements classified as class 1. So these two are generally different. And now that we have recall and precision, we're going to go for F-measure, and F-measure is nothing else than the harmonic mean of the two. By giving equal weights to 2p and r, it's 2pr divided by p plus r. Now, you can give different weights to precision or to recall depending on what is most important for your study. This kind of F-measure, it's called F-beta, where beta is a non-negative value that acts at the weight. Here, instead of 2, we include 1 plus beta squared, and beta squared is accompanying p. For example, F2, if beta is a 2 here, gives twice the weight on precision, and F0.5 gives half the weight on precision. Now, there are other classification methods. These ones were probably the most interesting for our course, but there are several other methods that definitely worth mentioning. First one is the decision tree, in which we divide the feature space into regions and successively classify them as good with only one feature available. So we divide the feature space into branches and we walk through one of them mostly. Next one is a support vector machine, in which we attempt to find a straight line or plane that separates the classes. That's kind of a generalization of linear discriminant analysis, right? Yeah, then we have some naive approaches based on Bayes' theorem for probability theory. We have neural networks. We have logistic regressions, which are interesting. It's a type of regression that is applied to categorical data. Yes or no, and it results in a classifier. The way this is optimized is generally using the most likelihood method, as that is simple enough and yields really good results. And well, this was it for this lecture. I will see you in the next one. Thank you for joining.